Okay, problems for chapter 27. First problem has to do with polarizers. Unpolarized light with intensity I0 is incident on a polarizer. A second polarizer is placed with its transmission axis at a 20-degree angle to the transmission axis of the first polarizer. A third polarizer is placed with its transmission axis at a 90-degree angle to the transmission axis of the first polarizer. Find the intensity of light that reaches the second and third polarizers as well as the intensity that exits the third polarizer. So, drawing a picture, I have initially unpolarized light. Of intensity I0. Now it's going to go through my first polarizer. So here's my first polarizer. And my first polarizer has a polarization axis that I'm just going to arbitrarily say vertical. So I'm going to say theta 1 equals 0 degrees, measuring from vertical. And so how much light comes through is the question. Well, the light that comes through is going to be vertically polarized. And it turns out that always, if you go from unpolarized light through a polarizer, you have I is equal to 1/2 of what you started with. That's just a rule. It's a rule that comes from integrating the intensity from 0 to, well, I can just use pi over 2 actually. I think it's 0 to pi over 2 of cosine squared theta d theta. That's all you're doing. Anyhow, we're not doing calculus here, so I am not going to make sure I did that right. I'm just going to move on. Now we have a second polarizer. That's an angle of theta 2 is equal to 20 degrees from the first one. So the light that comes through this is now going to be polarized in this direction. And so to get this, we just use the law of Malus. Now notice I put theta 2 minus theta 1. It's the difference between those two polarization angles. So that's going to be equal to 1/2 I0 times cosine squared of 20 degrees minus 0, which comes out to be, and I just did this calculation, 0.4415. Obviously, we didn't have any defined significant digits for anything here. It could be infinite for all we know. So I'm just putting 4 here and being good. So that's I2. And now we have our final polarizer. Our final polarizer theta 3 is equal to 90 degrees. And so the light that comes out of this is going to be polarized like this. And what's I3? The knee-jerk reaction is to say, okay, now we started with vertical, we ended with horizontal. You had none, horizontal has none vertical. But the middle one, as we saw in lab, changes the light. So we're just going to have the law of Malus again is equal to I2 cosine squared of theta 3 minus theta 2. So that's 0.4415 theta 0 times cosine squared of 90 degrees minus 20 degrees, which is 70 degrees. And that comes out to be 0.0516 theta 0. So there's our answers. So we have 0.500. Let's zoom in so I can write a little better. 0.4415 and 0.0516. Right, so those polarizer problems, they're actually not very hard using that law of Malus. What was making this one a bigger problem was simply that you had to worry about, okay, so the first polarizer blocks half of the light if it's unpolarized. If it had already been polarized, we would have had to jump straight to the law of malice. So don't just always say blocks half. If it's already polarized, you go to the law of malice. And then we use the law of malice for the angle between adjacent polarizers. Now, a ruby laser produces 694.3 nanometer beam of light. Find the angles for all possible diffraction maxima if the light goes through a diffraction grating with 600 slits per millimeter. So this is the same slit that we used in lab. So we have, here's our laser beam, here's our diffraction grating, and then coming out of that diffraction grating, we're going to have well, let's be a little more realistic. And so this is n equals 2, n equals 1, n equals 0, n equals -1, which is symmetrical. So I don't need to do the -1 and -2 because they're the same as +1 and +2. And potentially more. In this problem, there aren't more, but potentially more. My equation is d sine theta is equal to, I called that n there, I should have called it m, just so we don't think index refraction, m lambda, where m is an integer. So solving for theta, theta subscript m is equal to arc sine of m lambda over d. So I just put in my numbers. Theta sub 0 is equal to a sine of 0 times 694.3 nanometers over my spacing, which is 1 millimeter divided by 600. And of course, arc sine of 0 times anything is going to be 0. So this angle theta 0 was 0 degrees. Theta 1, let's change colors for theta 1. Theta 1 is equal to a sine, and I'm going to calculate over here, 694.3 nanometers divided by 1 millimeter over 600 is equal to 694.3 times 10 to the minus 9 meters times 600 divided by 10 to the minus 3 meters. And so, believe it or not, I didn't actually calculate that before. I really should have. Equals that. How did I screw that up? Okay, so that should be equals 4.166 times 10 to the minus 7 with no units. Really, Richard? Really? I don't think so. Where did I mess that up now? Okay, 694. Wow. I am really failing at math. 694.3 nanometers. That's 10 to the minus 6 times 600. Yeah, that's what I did. Okay, more like it. 0.4166. And this was n equals 1, so times 1, or m equals 1, so times 1. And so that gives us 24.6 degrees. And then for m equals 2, That gives us 56.4 degrees. And then going to theta equals 3. And now we have an oops moment, because 3 times 0.4166 is bigger than 1. But sine can't go anywhere beyond -1 to +1, so this doesn't exist. And once we get to doesn't exist, we don't need to go further. So there we have it. We only have 0, 24.6 plus and minus, and 56.4 plus and minus for the diffraction peaks, just like we saw in lab, because in lab we did 632.8, which was pretty close to the Ruby. It's, they're both red. All right. Hope you're ready for the test.